Okay, standard cell potentials. Once again, E naught, the naught represents some sort of standardized conditions. And if the redox reaction involves a gas, then we're dealing with 1 atmosphere standard pressure and 1 molar concentrations for solutions, which means that, we have some issues here with ideal behavior. So we want to keep the concentrations fairly low, although 1 molar in a human system is actually a pretty high concentration. But anyway, so under these conditions, what is the voltage? Now, the voltage is a measurement of driving force. The more positive the voltage, the stronger the driving force is to reach equilibria in the forward direction. If you have a negative cell voltage, then the reverse reaction would drive forward. So again, voltage being a measurement of, hey, how far away from equilibria are we? They introduced standard reduction potentials, and there's actually two charts that they could give you. They generally give you reduction potentials, but they could also give you oxidation potentials, in which everything that I'm going to say on an oxidation potential is the exact opposite. So in a reduction potential, first of all, on the left side, we're dealing with reduction half reactions. So fluorine becomes fluoride, and this has a very strong driving force. So the voltage is positive 2.87 volts. Again, the higher, the more positive the voltage, the stronger the tendency is for that thing to happen. Now, it doesn't mean that the opposite can't happen. We can certainly take fluoride and turn it into fluorine gas. All you have to do is hook up a battery and pump 2.87 volts, a voltage battery, and pump electrical energy into it to get that to happen. So the positive values means there is a strong driving force for reduction, and the negative values at the bottom of the chart means that there's a strong driving force for oxidation. Hang on just a second. Okay, sorry about that. Okay, so from that table, when you're looking at driving forces, you can't take half a reaction and separate it. What they do is they look at the results of a reaction and they say, well, let's compare everything to a standard. So they chose the H plus reduction, acid to hydrogen gas. We're going to set that as the standard at 0 volts, and then we're going to compare everything to it. Now they didn't have to pick H plus. They did. I mean, we could certainly set tables based upon something else being the arbitrary value at 0, and then everything else would get adjusted accordingly. For instance, if we had chose the zinc reduction as the arbitrary set of 0, then everything would have been adjusted by 0.762 volts. When you calculate a reaction, you add the reduction potential to the oxidation potential to get the overall cell potential, E naught. You would still get the same value, regardless of whatever you set at 0. Again, these are all comparative values. If they give you reduction potentials, you can get oxidation potentials. It's the reverse reaction, so you just reverse the sign. Now, this is not stoichiometric. Delta H is stoichiometric. Remember, with delta H, if we did the reverse reaction, we just took the opposite sign, but we multiply it by the number of moles in the reaction. Here, voltages don't change. Again, it's a measurement of driving force regardless of the stoichiometric output. All right, so if we look up the reduction potential for copper, we'll find that it is positive 0.339 volts. So the oxidation potential is the opposite of that, negative 0.339 volts. From a reduction potential chart, besides driving force, you can take a look at the strength of oxidizing and reducing agents. Remember, if something has a strong tendency to reduce, if it is a reducer, it makes something else oxidize. So we can have two terms for the same chemical. We can call it a reducer or an oxidizing agent. Something that has a strong tendency to oxidize, we can call an oxidizer, but it also causes something else to reduce, which makes it a reducing agent. So the stronger the tendency is for something to reduce, the stronger it is an oxidizing agent. It's going to make something else oxidize. Now, the interesting thing is, if you take two things that normally reduce and put them together, one of them will be the driving force over the other. The one with the larger reduction potential will reduce, but it's going to cause the other material to oxidize. So as far as reducing agents, if they give us a reduction table, we can just take the opposite. We can take a look at the more positive the oxidation potential is. That makes it a strong reducing agent. And this is true for a reduction potential table, but it would be the opposite for an oxidation potential table. I'm not going to use an oxidation potential table. They don't use it on the AP exam. If we were back in the classroom, that big poster I have hanging up on the side wall has oxidation potentials, and I kind of like to use both of them together so that you get used to using both of them, but we're just going to focus on reduction potentials. All right, so the overall cell potential is the oxidation potential plus the reduction potential. So again, look at these two chemicals. Chlorine, which is, again, it's stable as a diatomic molecule, but tends to be more stable as chloride ions because it picks up that extra electron and it has its own extra electron, which makes it a stable octet. Now, it's a stable octet as a chlorine diatomic molecule also, but it's more stable as a chloride ion. And we could say the same thing for bromine. Bromine tends to be more stable as bromide. These are things that are highly electronegative, so they tend to take on a negative charge. So they tend to reduce. However, if you react chlorine and bromine together, they both can't reduce. One thing has to oxidize. So the chlorine has the stronger driving force. If you look up its reduction potential, it's 1.36 volts. If you look at the reduction potential for bromine, it's 1.077 volts. So what's going to happen is the chlorine is going to, in essence, force the bromine to oxidize. So you're going to get chlorine becoming chloride, bromide becoming bromine. And we actually did this lab earlier in the year when we did our redox, our activity series. Add the two potentials together and we still get a pretty large voltage of positive 2.83. We're going to find out that anything above positive 0.1 is a pretty strong driving force. Doesn't mean it's stoichiometric, just means it's pretty strong driving force. And this I already said. Okay, determination of a reaction. Remember, with transition metals like tin, we said that they normally have multiple oxidation states which are stable. Tin is stable as a 2 plus ion. It is stable as a 4 plus ion. It is also stable as neutral metal. So what happens when they give you a reaction like this is you can look up the reduction potentials to predict what's going to happen to the tin 2 ion. Is the tin 2 ion going to oxidize and become tin 4, or is it going to reduce and become tin metal? So let's take a look at that. Why do I study electrochem? To increase my potential. Okay. So we said we're going to react tin to chloride with bromine. How soon I forget. Yes. So we said with tin 2 chloride, in an aqueous solution, you're really looking at these two ions. And bromine, we're going to write diatomic bromide. All right, so tin can either oxidize and become tin 4, or it could reduce and become tin metal. chloride, that is only, you can't make it more negative. There's no -2 charge for chlorine. There's no -3 charge for chlorine. So you can't reduce chloride, but you could oxidize it and get diatomic chlorine. Bromine doesn't form a positive cation, so you can't oxidize it, but you could reduce it and get bromide. So what's going to happen here depends upon what's going to happen to the tin 2+ ion. So we say, all right, what are our potential oxidations? What are our potential reductions? Okay. Well, one of the reductions is that tin 2 could become tin metal. Of course, we would have to add 2 electrons to make that happen. So we look up our reduction potential for that. Tin 2 becoming tin metal. Here it is right here. Tin 2 becoming tin metal is negative 0.14 volts. So not likely to happen. However, it could happen if chloride is a really strong oxidizer. If chloride has a really large tendency to oxidize, it could make tin 2+ become tin. Let's take a look at the oxidation potential for tin 2 becoming, oopsie poopsie, tin 4 plus 2 electrons. So again, I go to my reduction potential, and I have the reduction of tin 4 becoming 2 electrons at its positive 0.15 volts. So that means the oxidation of that is going to be negative 0.15. So tin doesn't want to do either of these things. However, it's going to have to do one or the other depending upon what the chloride reduction potential is or the bromine oxidation potential. So let's take a look at the chloride reduction potential, and we already know this is going to be a very large value. Chloride oxidation is going to be a very low value. The reduction of bromide is going to be a very large value. Sorry. So let's take a look at, bromide becoming 2 bromines. We'd have to add 2 electrons to do that. So we look up the reduction of bromine. All right, so here it is. And we follow that over, we get positive 0.1066. So a very strong driving force for bromine becoming bromide. And then our last oxidation would be, well, what if we take 2 chloride and produce diatomic chlorine plus 2 electrons on this oxidation? Again, we go and we look up the potential. The reduction of chlorine is positive 1.358, so this is going to be negative 0.1358 for its oxidation. All right, so we have to pick the driving force here. The driving force is the reduction of bromine to bromide. And that means between the 2 oxidations that can occur, we pick the one that has the least amount of resistance to oxidation, which is tin 2+ becoming tin 4. So when we write the reaction, all right, so we start with tin chloride, and we're going to react that with bromine, and that's going to create tin 4 and 2 bromides. Now I got rid of chloride because chloride is not oxidizing, chloride's not reducing. That makes chloride a spectator in this case, so it's out. And as far as redox reaction balancing, we just look to see if the atoms are balanced. They are. And then the charges, we have a positive 2 charge on both sides, so we don't have to do that whole AEIOU thing. And now we just add the reduction potential to the oxidation potential. So E0 is equal to E read plus EOX. And this comes out to be 1.066 volts. Hey. And we're going to add that to negative 0.15 volts for the oxidation of the tin. And that's going to give us 1.051 volts for E naught. All right, so let's see how they worked it out. Again, their reduction potentials are a little different because this slideshow was originally made in 2002. So the values are slightly different. But again, they look at the oxidations. Tin does not want to become tin 4, but we're going to make it become tin 4. Chloride does not have a tendency to naturally want to become chlorine, but it is possible. And for the reduction potentials, again, tin 2 doesn't want to become tin metal. However, there is an extremely strong driving force for bromine becoming bromide, and that's what pushes the reaction forward. So we're going to pick the bromine becoming bromide reduction, and the one with the least resistance is going to be tin 2 becoming tin 4. And when we put that together, we get this reaction. And again, slightly different voltage because slightly different reduction potential chart. All right, in the next one, we're going to take a look at Gibbs free energy and how that relates to voltage. And we'll take a look at KEQ and how that relates to voltage. Again, voltage is a measurement of strong driving force. So certainly we could take a look at how much energy we can harvest from that driving force. And we can take a look at the position of the equilibrium.